Okay, so it's already time. So welcome to the next lecture from Effective Software. Today I will talk about memory analysis. Specifically, we will talk about static and dynamic analysis. Then I will point out the difference between shallow and retain size while using tools for the memory analysis. Then in the middle part, I will talk about data structures, how they are organized in Java Virtual Machine, what is autoboxing, unboxing. And at the last part, I will talk about memory usage efficiency and present you collections for performance. So if we talk about performance factors, usually we think about two things: total runtime and memory consumption. Total runtime of your application is mainly affected by the internal algorithms or program used, what is the complexity of that algorithm, how many instructions you generate, if you use synchronization and other stuff. That's one factor affecting total runtime. But as already mentioned last time and the previous times, memory management in case of Java Virtual Machine plays key role as well, because there is an overhead related to the memory management, specifically garbage collection times. Usually that garbage collection happens in stop the world fashion, and your application is not running when a garbage collection is running. So if you generate a lot of objects, then it increases pressure on garbage collection, and then it slows down your application. And finally, data structures themselves affect also the total runtime of your application because of speed of data access, whether you have some complex hierarchical data structures which requires a lot of memory translation to get to the data. And as you can imagine, the size and complexity of your data structure is clearly related to the cache efficiency usage. If you have smaller data structures, they can better fit into caches in processors, in the cores, especially if your data structure fits, or a lot of data structure fits into L1 data cache. That's the major booster for your application. Data structure and its composition also affects the memory consumption. And the term I will define later, that's the memory usage efficiency. So today we will focus on the memory aspect of your applications. There are two approaches for analysis of memory of your application. First is static and the second is dynamic. So in the static analysis, you analyze usually memory usage at some given moment. So you stop the application or pause the application, and you analyze what is currently in the memory, what are the data structures are there, you can inspect the content, you can do the efficiency analysis, you can study how your data structures are complex. That's very good approach. Another one is dynamic aspect. In dynamic aspect, you analyze dynamic changes over the time, because usually a lot of objects are created during runtime. That's normal, and it's changing over the time. And here you study the change of usage of the memory. You also usually study whether you have a memory leak situation, where you have consuming a memory with some usually big data structures, which are no longer needed by your application. So let's look for available tooling at the moment. So start with the static memory analysis. The basic approach is to study object histogram. That's the simplest approach you can take. So you simply analyze histogram of objects. Here is one such output of a histogram. You see here various classes and the number of instances in this column. and total consumption of bytes related to those instances. So you see here we have object-based integers, hash map node structures, linked list node structures, and others. And you can then focus your analysis in the code where you usually use this kind of data structures in your application. If you would like to study a histogram of objects, you can do it simply using JMap tool, which is available along with the Java Development Kit. If you install it, there is this option, PID is a process ID, and this kind of thing generates this output. If you run that, it implies global save point. I've already talked, I think, 2 courses back about save points. So it stops your application, then traverse the heap and computes this histogram. Another thing you can do is a heap dump. You can capture current snapshot of the heap structure. Again, it's imply global save point, but instead of computing just the histogram of objects, in this case, you are dumping everything out of the memory. That heap dump can be created automatically if there is out-of-memory error using this option. By default, it is not created. Or again, you can use JMap tool where you can specify whether you would like to dump only a live object. Live mean reachable objects which are somehow reachable from your application, or all objects, even those which were created recently and are not collected yet. So you can distinguish between that, or you can use more advanced tooling, which is usually the case, Visual VM, open source tool, or EuroKit. It's without license or easy license if it's used for non-commercial usage. And then you need to use some kind of tool to analyze the created dump, because dump is some kind of binary format of your content of that heap. So if you use Visual VM, which is the image here, you can then see per object how many size is consumed, how many retain size, how many shallow size. I will describe the difference between these two on the next slide. So let's look here. Within that tooling, you can also inspect the current content of the object. So you can go and see in your structure what are the values there. That's possible. So about the difference between shallow and retain size. Shallow size is the size of the memory consumed directly by the object. You already know that the object representation in the heap has some kind of header information. So that's included in the shallow size. Just that object. If that object contains references to others, this shallow size compute is computed just the memory consumed by that reference itself, storing that reference. You already know that there exists OOP, ordinary objects pointers, or compressed OOPs. So depending on the heap size, the reference consume 8 bytes or 4 bytes of the memory. On the other hand, retain size is more complex thing. So let's illustrate it on this image. Let's start with this right image first. Here we have GC root. Arrows means references, pointers in C world. So GC root stands for all the set of all possible initial references. Those could be static variables or local variables. Inputs to methods are also GC roots for this aspect. So for example, here we have some local variable which is a pointer to the object 1. This is a pointer. Object 1 contains 2 references. One goes to object 5, another one goes to object 2. There is also reference from somewhere different, from different GC root to object 5. Object 2 contains another 2 references to object 4 and object 3 down the right side. But there is no other reference to them, so you don't see any incoming arrow to those objects here. So if we now define retain size for object 1, that would include shallow size of all blue objects. All blue all together. Why? because those objects are reachable only because of that object. If the object 1 doesn't exist, these object 2 and also descending objects are no longer reachable, so there can be collected by garbage collection cycle. So those object 2, 3, and 4 are reachable only because of object 1. That's the reason why they are included in the retain size of object 1. So it's sum of these 4 blue boxes together of their shallow size. There is not included object 5 because there is another incoming reference. So if we discard this reference here between GC root and object 1, this is collected and this will remain. So if you sum all remain size of all objects, it will sum up into all consumed memory because every object is there just once. The difference here is that we added just this arrow into object 3. In that case, object 3 shallow size is not included into retain size of object 1 because it is standing itself. So that's the difference between shallow and retain size. On other word, retain size is always bigger than shallow or the same like shallow. If you have retain size for the object which doesn't have any reference, it's exactly the same like shallow size. This tooling, which allows you to open heap dumps, usually contains tools where you can analyze the memory snapshot itself. And you can study whether you waste memory or not. By wasting, we mean that you are consuming memory by something which is useless, usually. For example, duplicate strings. You have a lot of string is immutable, and you have a lot of string instances which contains exactly the same content. In such case, you should consider pooling or interning. Intern is an internal feature of the virtual machine, which does the pooling of the string objects based on their content. The same is applicable to any general objects, duplicate objects. They have the same content of all fields. Again, you should consider sharing them or perform lazy creation, create once they are needed, not keep them forever, etc. Another common mistake is zero length arrays. You are creating array list or your own native arrays, which doesn't contain any useful content, but just the fact that you have that array defined, it implies that you have object header for that array and also reserve space for the whole content of that array. Again, you are implying unnecessary load for your garbage collection. You should, in such case, if this is your case in your application, you should consider using empty array singletons. So some single instance, only one in the whole JVM process, which will be used for empty array. And anytime you would like to use that array, you just check, is that singleton? Yes, okay, that means it's empty. I don't need to check anything else. By the way, this singleton empty array is used in recent Java in array list, not in other frameworks. I will talk about that later. Same applies to null fields. You have a lot of objects which are very complex, contains a lot of references, but usually, or primitives, doesn't need to be reference, but usually doesn't contain any useful value. In such case, you should consider usage a special object and use subclassing if you need those fields. If not, just create some simplified object without the fields. Special category is sparse array. Sparse arrays is a term where you have large arrays which are usually empty or contains large blocks of nulls, zero, or same elements content. You should use alternate data structure maps or other in this case. And finally, inefficient data structures. There is a large overhead of, again, some useless content inside. you should consider refactoring of that data structure. I've already defined memory leak situation. How that can happen? It can happen either explicitly, where you create object but not using in your application, and that object, and you have reference for that. It's consuming all the time the memory not used. In such case, you should consider a lazy initialization. I've already mentioned that. Another option is, it is very, very popular to create anonymous implementation of some interfaces, like, for example, run and interface runner, for example, or callable with call method. If you have anonymous implementation of the code, or you are creating a Lambda function, which implies, in fact, anonymous implementation as well, that anonymous implementation contains implicit back reference from the inner class, from the internal, to the enclosing class automatically. Even you haven't specified there any field, that back reference to the this of enclosing class is there automatically. So if you pass that runnable or callable into thread pool or some framework and register that as some callback listener or whatever, doesn't need to be runnable, could be anything, it implies that if that framework registers just the reference to the past implementation of runnable, callable, whatever, it automatically means there is one strong reference to that implementation, anonymous implementation, but that anonymous implementation contains automatically reference to enclosing class. And that prevents collection of that enclosing instance, and also all the reference content as well. Even you don't have that implicitly in your code. So you should minimize usage of these non-static inner class instances. And finally, some advanced tooling also are able to analyze performance of your data structures, performance from the perspective of read-write access. For example, if you have hash tables, hash sets, hash maps, it checks uniformity of the distribution of the hash codes over the hash table. If you have wrongly defined hash codes for your objects, there is a lot of collisions, and it creates a linked list internally and doesn't use effect of the hash table data structure. So let's move to the dynamic memory analysis. The simplest way is look to the garbage collection telemetry. You can use that visual VM with the visual GC plugin or other tooling. It will provide you this kind of charts. On the x-axis, you have usually time. On the y-axis, you usually have time consumed, so delay. So here you can see that the overall GC time contains 11 garbage collection cycles, and it consumes 4 seconds of your application. Usually, depending on the configuration of garbage collection, this means that's the time when it was not running at all, because there is the stop the vault of your application. And then you can analyze the hidden space content, survivor spaces. This is not the time, this is the consumption of the hidden space, and also old generation consumption. So you usually see this saw pattern where you are creating a lot of objects. If there is no more space, it triggers garbage collection. This is here. And garbage collection results into usually emptying hidden space, copying survived data into old generation or into one of the survivor spaces. So by this, you can analyze how much your application creates new objects, because you will see frequent garbage collection cycles. That's the simplest way without any additional cost when analyzing your application. Another option is you can create heap dumps. Not the single one, like I've described in static analysis, but in this case, sequence of heap dumps in various moments. And then usually the tooling for analyzing heap dumps allows also to analyze a difference between those heap dumps. So then you can see what is the difference from the second, third, how many object instances of particular types are created in between, what was implied in the size. By that, if you sample several times, you can analyze a dynamic aspect of your application and consider changing some data structures or approach to create new objects. The fine-tuned approach is allocation tracking. I've already talked about that while I was presenting CPU aspect of the analysis, where we were talking about sampling and tracing. And I've already said, okay, if you enable tracing, it implies code change and affects all optimization techniques. The same is applied here. If you enable allocation tracking for memory analysis, it instruments your code to track every new in your code. You can specify a filter. That's a good approach usually. Just focus that tracing to objects, to candidates you identified in histogram analysis or elsewhere. And also you can specify, I don't want to track all allocation, but only every nth allocation to reduce the amount, because every time internally that instrumentation, you can imagine that if you need to capture that new object is allocated, you need capture where, which type of object. So there are some map structures. You need analyze stack with frames where from which part of the code that allocation was caused. Because then if you look to the tooling, you can then click and see what was allocated and exactly where. So you see the stack, exactly the stack pointing to your source code, where that allocation happens and how many times and what the overall size was, and also you can go deep even to the content of those objects. But this kind of analysis affects the performance of the application at that moment. I've already said that CPU tracing implies issues to application of some optimization techniques. In this case, it's exactly the same. So you can start and allocate tracking of some object, but finally it can happen that if there is no allocation tracking enabled, there is that escape analysis optimization technique implying that the object is not created at all. So theoretically, by enabling allocation tracking, you can cause that this optimization technique is not in place, and you can measure something, some allocations, which are not happening at standard runtime at all. And that's the problem. There is one simplified way what you can do. You can use GMC tool, that stands for Java Mission Control, which includes a flight recording. Flight recording implies that there is no special bytecode instrumentation needed at all, but rather it uses already some internal statistics which are collected anyway inside Java Virtual Machine at some particular moments. It's not full allocation tracking, but it's relating to TLAB, which stands for Thread Allocation Buffer. I've already shown the code how it looks like when you allocate new object. It first tries to allocate a size related to that object inside thread allocation buffer, thread specific buffer on the heap, just for that thread, which doesn't require any cross thread synchronization at all. If that is possible, that's the fastest way, because that buffer is just yours. You doesn't need to synchronize with anyone. But if there is no more space in that buffer, because the object is larger or it was already consumed, there is a call into internal of the virtual machine. And during that moment, this flight recording can occur. So if it is enabled during that call, internals of the virtual machine already knows what kind of object is requested to be allocated, what is the size of the object, and also it can easily track from which part of your application it was called. So here you can see the output of such flight recording of the GMC tool on some testing application. You can see that there were almost 400 TLAB allocations. The size of that TLAB is dynamic, so there is some minimum, some maximum, some average. You can see how many total thread allocation buffers were created. You see here almost 1 gigabyte. You have also statistics about number of objects which cannot fit the thread allocation buffer at all because they are very big, for 48 in our case. What was the size, what is the amount, etc. And here you have a timeline with the instances of such allocation. Green are thread allocation buffer allocations, red are objects which cannot fit thread allocation buffer at all. But there are additional tabs here. So if I progress to next slide, you see this is the second tab. This is related to allocations which cause request for new TLAB. So you know what kind of object it was, what was the size. If you click to the object, you see the stack from which place that object were requested. So you can use this tool to provide to do some kind of sampling analysis of the object allocation, like a sampling for the CPU. The final tab here is the same information, but just for the objects which cannot fit the TLAB at all. So in this case, you can see there are allocated like 100 megabytes objects, etc., etc. And again, you see also from which place it was allocated. So let's move to the next part of the presentation. Data structures. The basic division of the data in the virtual machine is that you have primitives and you have objects. You should know all kind of primitives. In brackets, you have their standard size in bytes. There doesn't require any implicit allocation, and usually they are stored in variables or as operands on the stack. After a C1 or C2 compilation, just-in-time compilation, there are mapped to registers usually. On the other hand, you have objects. Objects are stored on heap, implies that there is object header, already presented several times, this gray header of the object. The minimum is 12 bytes, another is 16 bytes for standard object. If it is array, it's bigger. Class is with K because it's internal pointer. 4 bytes are for compressed OP, so heap size smaller than 32 gigabyte. 8 bytes are for heap size larger. All objects are by default automatically instances of objects, descendant class of object, and thus contains these standard methods. Doesn't matter if you override them or not. I've already talked last time about hashcode. Hashcode itself is stored in the mark word to have it stable. For every primitive object, there exists object-based representative, just with the capital letter. In this case, they are consuming much more than the bytes we just mentioned here. If you have a generic object, just not this simple, internally the data are organized using this type group alignment, where the padding, where it tries to store longs, double first, then ints, so simply from largest to smallest. With one exception, references are at the end of the object. That's optimization for the garbage collection. to have it close to the next object header. So if we look to specific example here, so let's have a structure object here with this definition, quite complex object with a lot of fields with various data types, primitives. There is one reference here, a second reference here. If we look to the representation on the heap, where the heap is smaller than 32 GB, so compressed OOP is used. This is how such object looks like on the heap. You can see that the size of this object is 4F in hexa, so 80 bytes decimal. And you can see that there is a collocation of longs doubles here. Even there are defined like here, here, and then down here. First, it tries to group them together with one exception, because there was a gap here, 4 bytes. So the first 4 byte or 2 byte or 1 byte content is inserted here. That was the integer one. And then filling with the 2 byte content, or 4 byte content, 2 byte content, 1 byte content, and finally the references are there. So that's how the content is organized. If we start exactly the same application with the same structure in the virtual machine with more than 32 GB, you can see how it changed the representation. Now it consumes 5F hexa size, which is 96 bytes decimal, more than 20% more versus previous. So just the way how you start your application affects how the data structures will consume the memory. So I've already mentioned that some time ago, that it hardly depends how many memory you need, because if you need just around 32 GB, fine. But if you, with XMX parameter, specify, I need 33, that's not good idea. Because usually 32 GB heap application, if you switch that to standard OOPs, it requires more than 40 GB, just because of this increase of the sizes. Okay, so arrays, special kind of objects with a special header, like here. There is one more field, array length. So the header is longer, 16 or 20 bytes, again, depending on the heap size. Java automatically check the limitation during the runtime. That's the index out of bound exception. Primitives are stored directly in this sequence. If there are references, references are here, following the header. If you have multidimensional arrays, that's represented as a rect array, which means array of array. You have top-level array with pointers, with references to another subsequent arrays for every element. So there is a huge overhead of the headers. For every sub-array, you have its own element, etc., etc. If it is three-dimensional array, it's even more complex. The access to such data structure is then affected because of the referencing. First, it has to go here to the top-level array, check what is the reference to the underlying array, then go to the underlying array, read the value or read the further reference to third layer, etc., etc. So in such case, you should consider flattened array, which means instead of creating multidimensional arrays, create single-dimensional array with larger size and compute indexes to that array yourself, like I multiply by j, and that's it. Faster. Much faster, because you don't have overhead for this subsequent array headers, and also you don't have that problem of the referencing at all. And the multiplication itself is extremely fast. in nowadays computers. So let's define memory efficiency measure as this equation. Division of the useful content size by retain size of the data structure multiplied by 100 to have it in percentage. So it means memory efficiency, if it is 100% efficient, there is zero overhead. If it is zero efficiency, it means there is no useful content at all in the data structure. This memory efficiency perfectly correlates with the cache efficiency usage because of the overhead. The cache line read always 64 bytes of the memory. On more recent computers, it could be even bigger than 64 bytes, 128 or so. And that is sequence of the memory. And if you fit more objects into that area, you better use your cache and you not waste it by many headers, etc., etc. Moreover, the data locality, if several objects fit into one cache line, it speeds up sequential processing of such objects because you have already data available in CPU, in L1 data cache. After accessing the first element, it reads the first element and also everything which is inside that 64 bytes. There could be another 10 elements, for example, inside. Those are then zero time access time. So if we summarize in this table memory efficiency of the basic object representation for standard types, from Boolean to double, you can see that, for example, for Boolean, useful content is 1 bit, true, false. Retain size for the smaller heap is 16 bytes, 12 byte header, 1 byte for Boolean. That's it. So if we compute memory efficiency, it's less than 1%. Everything else is overhead. It's even worse for larger heaps, around 0.5% only. It's getting better and better up to the long or double, where you simply have data like 8 bytes only, but the retain size is 24 bytes in both cases, so it's 1/3 efficiency in this case. So still very inefficient if you used object-based representation of standard numbers. Related to the standard object-based representative for primitives, there exist these two terms, autoboxing and unboxing, which happens automatically during assignment and parameter passing, and internally they are using value of and int value or whatever type of primitive it is, methods inside. So if you look to this simple code, like we have primitive object class here, which contains one field, object-based integer with capital I, originally 0, and then we have main method which just does increment of that value. So if you look to the bytecode using the bytecode representation here, you can see that there is a static initialization block, that's for this equals 0 initially, which calls value of with 0, and the result is stored into that integer field. So even during the static initialization block, auto-boxing of that 0 happens, because that 0 value needs to be converted to object. And that's this value of. If we do look to the main method, which just does the increment of that value, it first needs to convert this reference to object-based integer into number. That's happened here using int value. So it calls on that instance int value method to convert that object into really the number, into the primitive. Then there is this 6 and 7 at 1, that's that increment. And when you have the resulting value, you need auto box that back to the object. Strange. That's very inefficient. That's happened here using, again, value of. So this is the process of unboxing. This is a process of auto-boxing. And that happens natively without anything. So you have this simple code, but if you look how it works, it's strange. So if you look to more complex example here, word count histogram. So let's have a main method with input arguments, and we would like to count a histogram of words provided as input arguments here. So what we will do here, okay, let's create a collection tmap structure here where the key will be the word itself, value will be count. And here is the problem. All these standard collections requires to work with the objects. So there is a string and there is an object-based integer. So then if we traverse for each of all input, we usually get the last value. If it was null, we are storing, okay, that's the first instance. If it was not null, we are incrementing by 1. Finally, we will dump the histogram outside. And here we have a lot of autoboxing, in this case unboxing, so the code is extremely inefficient. If the word list is 1 million length, for example, it will be extremely slow. So let's look to another example. Let's have this code somewhere from top to down. I and j, in this case primitives, both initialized to value 2. Then let's create array list, type to the object-based integer, because you cannot type it to anything else. Add I, add j. Now we have a sequence of printouts, printing boolean true false. Of what? Of the input argument. So I equals j. What will be output here? Both have value 2. What do you expect? True false? True, yeah, that's correct. What about the second case? List get element 0 equals list get element 1. True, false. Why? We are comparing references. That's good idea, but there is an exception. In this case, it will be true. Exactly. There is identity semantics inside some kind of primitives, which guarantees that there is no waste of memory on the same value and returns exactly same instance. If you autobox number 2, you get instance for 2. If you autobox number 2, you get exactly the same instance. So in this case, we are not testing value, but rather we are testing references, but they are same, so it's true as well. And finally, we call equals method on the object-based integer, and that's for sure implemented correctly, so that's true as well. But if we change that I and j for much larger number, like 2000, this will be again true, this will be again true, and the middle case will be false, like you mentioned, because that identity semantic is limited. It is done just for some limited amount of numbers, and as you mentioned correctly, it's done for up to 127 inclusive from minus 128. So for short integers and longs, there is internal identity caching of this range. For bytes, it's unsigned, cache all values. For characters, it caches 0 to 127. It's not working, that internal cache, if you create your object yourself using constructor like this. So if you call new integer with the initialization 1, there is no caching. You get new instance. So if you have a cycle, million of iteration, you get million instances with 1. If you use autoboxing, that's the reason why there is that autoboxing using value of. Value of is static method, so factory method of the integer. And it has to return short. but it's not the constructor yet. So using this provided primitive, it can do the lookup into cache and return value from the cache. If it is not matching the cache, it can create using the constructor new instance. The cache itself is initialized in this static initialization block here. This is static initialization block. Initialize when for the first time there is referenced short cache is created. So 256 objects are automatically created, even not used anywhere. Unboxing is here, just returns the value. So what you can notice, that there is no identity semantics caching for doubles and different types than listed here. So if you use doubles in your application with capital D, object-based doubles, and you have a lot of same values, you are consuming a lot of memory. Same is applicable to integers outside of this bound, of this range. You can affect the size, but not for all data types. The upper limit can be affected. There is a startup attribute where you can define that that cache should be larger or smaller for specific usage. But it's not used for the short. It's used, I think, for integer and long only. So let's look to more complex data structures like linked list, array list, and hash map. These are the standard collections included in Java. Linked lists internally use automatically linked list.node, which is typed and supports bidirectional list, next, previous. So you can easily go to the next element or previous element just by the reference. So this is just the enclosing class having the reference to the provided value and also to the next node and previous node. That's it. Array list contains, on the other hand, backend array with object type in this case, because that's typed class. So there are references to those objects. So anytime you are using these standard collections, it implies autoboxing. So if you put there just the numbers or whatever, those are converted to objects using identity semantics. If it is outside the range, new objects are created, and all these data structures collections contains just the reference to those objects. That's crazy and very inefficient. Hash map, by the way, use internal node structure with key value as well, or sometimes map entry, depends on the implementation, where key is a reference to object, value reference to objects, and contains a linked list, a single list in this case, to solve collisions in the hash table I've mentioned. So if we now look to the example where we measure 1 million of elements inserted in these standard collections, to simplify that, just the integers, million integers inserted in this standard collection, we can study the memory efficiency in this case. So what is the useful size? 1 million integers, integer is 4 bytes, so 4 millions, MI, millions, not the mega. That's the million really. 4 millions in case of a hash map where we have integer as a key and double as a value, integer, double, 12 million size. What is the retain size? For smaller heaps, you have it here. What is the efficiency? Less than 12% in case of linked list. You should think, okay, array list will be better because there is array list backend. Less than 23% only. So the remaining is useful. And that implies that you are inefficiently using the caches in your processor, because it doesn't mean that the remaining is empty or not used at all. No, there are headers, there are all this enclosing overhead, and those are used every time you are accessing the data. So it's even slow when you are accessing the data, not only wasting the cache. And in a hash map, less than 18%. Situation is even worse for larger heaps. You can see 3% decrease here, here more than 7, and here also some percentage is decreased. So it's very inefficient. So what you can do to work efficiently with such data structures, where you put usually the primitives, you can use collections for performance. I just mentioned 2 frameworks here, but there exists for sure much more. One of them is Trove, and the other is Fast Utils. This goes from Apache. This is lesser GNU published license. So depending on your use case, you should consider which one you are going to use. But it is allowed even for commercial purposes to use, for example, Trove usually. And this collections tries to avoid that inefficiency of memory representation by using type-specific maps, sets, lists, and queues. So instead of having, if you have, for example, array list data structure, which have backend array, but in case of standard array list, it contains array of references to objects. You cannot put the primitive. In this case, in type-specific, it's an array of that primitive. So instead of references, value is stored directly in that. They have much smaller memory footprint, so better caching. Sequential access is extremely faster than before because those objects before are not stored in sequence. Those are stored by the allocation time, and that could be really scattered over the whole memory. So in this case, it's really in sequence, and all that data locality I've mentioned applies here because you preload automatically 64 bytes of the cache line size. So all those numbers are already available. So it has fast access and insertion. In case of maps, it's using open addressing mechanism. I will talk about that on the next slide. In case of fast util, it supports big collections, bigger than 2 power 31, because I've mentioned that the standard array representation header contains those 4 bytes for the number of elements. 4 bytes, 2 power 32. There is some reserved for empty and others, so it's effectively 2 power 31 only. 1 bit is used for something else. So if you need larger array, FastUtil is providing you how to work with that. It also, this collection for performance support custom hashing strategies, for example, in Trove. Here we have some simple example. Let's create 2 character arrays with three letters only, A, B, C. Let's create 2 foo and bar, and then do the check. Is hash code of foo and bar equals? What do you think? Both are ABC. Yes, no, true, false. Yes, you mean no. Why? Because this is native array. Every object in Java is descending from the standard object. That object is implementing hash code. Here is no override of the hash code implementation. So the standard hash code implementation in that object uses the initial address where the object is stored to generate initial hash code value. These are 2 separate objects, 2 different hash codes. And if a hash code is different, then also equals, because there is that equals contract, which says 2 objects can be equal only if their hash code is equal and all elements are equal. Okay, here we break that those hash codes are not equal. Equals must return not equal as well, even though those objects are exactly the same. The problem is that hashing, that thing which returns hash code, cannot be overridden in this standard arrays. That's the problem with the standard arrays. So let's look to the open addressing. So you can imagine how it works for array list. Easy. Instead of pointers to objects, there are just the primitives in those arrays. Fine. for the linked list, instead of having internal node, which have again pointer to the object, there is directly that value. Fine. But how it can work for the hash map? So in standard hash map, there is that map entry or map node with key value, wrapper supporting the chaining for collisions. In this case, instead of using a hash table, which is the pointer to map entry object on those position, use type-based key array and value array. So if you have hash map or the map where the key is primitive integer and value is double, then there is integer array directly for the key and double array directly for the value. You reduce need for the map entry, overhead 1. You reduce another need for the auto-boxing, because primitives are stored directly. Another references are not there. Fine. But what about chaining? That's one problem. Another problem, what about empty elements? Because in the standard map, you have hash table, and if there is null, it means empty. There is nothing. Okay, what is null here? There are two approaches. Trove use another array, so third array, called as a state array. It's byte, so it contains a number of elements, size of the hash table, multiplied by 1, which has this constants, free, full, or remove information. Consume a little bit more memory. Or in case of fast utils, which is using just two arrays only for the key and value, there is a special tracking for empty, which can be modified. By default, it's 0 and or null if it is a reference, used for empty. So it means that if you would like to put mapping from 0 to something else, to some double value, you cannot, because that 0 is simply excluded value. You can exclude whatever you want, just for to save memory needed for the state array. That's the approach for the fast util, so you need to count with this problem. Also, this collection for performance sometimes use a different default load factor. The standard collection, standard hash map, use 0.75 load factor. It implies what's this the moment when resizing of hash table happens. What is the load of that? In this case, Trove has 0.5 only to reduce amount of conflicts, collisions. So how collisions are resolved in this case? In case of standard collection, chaining is supported by entry object, special new object for every key pair. That's not possible here. Here, it's using different approaches, either linear probing for fast util, which means if I have collision, there is already some element on this key value index. There is already some. Let's use the next one. If it is already used, let's use another next one, and so on. If I get to the end, let's cycle from the beginning. So that's the linear probing approach, which implies better cache utilization, because as mentioned, if you are reading data and then it found, okay, hash code of this element is not equaling what was requested for the get, you need look to the next element until you will found the end of that collision chain and say, oh, no, that element is not inserted. And because of you using linear probing, everything is usually already available in the cache line, so it's much faster. On the other hand, Trove is using double hashing approach, which has much less conflicts. It's mathematically proven than if you use two or more hashing strategies where those hash functions are not linearly dependent. So it's not something like the hash 2 is not, for example, 2 times hash 1, because it doesn't make sense. It's clearly linearly independent. Then it first uses hash 1 for indexing. If there is a conflict, add #2 value to that of the same element. And if there is another conflict, there is this I index. Finally, modulo dimension of T is dimension of the hash table size, because you need fit inside. And this is less conflict generating thing, even for more complex scenarios, because you are using at least 2 hash functions. On the other hand, it's not that efficient from the real implementation of the processors, of the nowadays processors. And for sure, definition of the hash function cannot be 0. Otherwise, it doesn't make sense. So the collision chains are stored directly in these arrays on different indexes. So you can now imagine, okay, but if I delete something or remove some element, there could be a conflict because I've created a gap, and then if I call a get, how it will know that we continue? That's what needs to be solved here, the complex deletion. And there are 2 approaches. Because of Trove is using third array, it tracks that something was removed. But in fact, it keeps the element in. So it never deletes the data, it keeps it in, just mark it as a removed. On the other hand, Trove doesn't have that removed flagged. So what it does, it traces over the chain, find the last colliding element, and move it into the position where it was removed. So that's the approach, what is used. Moreover, what is the size of backend hash tables? For Trove, because it tries to work with the best mathematical approach to the hashing, using this double hash probing, etc. It found, okay, if the hash table size is a prime number, that's the best what I can do. Because there is this modulo, and that is proven to be best to use the sizes of the hash tables, which are prime numbers. So you can look to the Trove implementation easily, because it's open source, and you can find how those prime numbers are fastly generated. On the other hand, fastutils used standard power of 2 because it used linear probing, power of 2 sizes of the hash tables. So now if we do the same comparison as before, 1 million elements stored in those structures. This is the standard structure, standard collection of Java, linked list with the capital integer. Identical one for Trove is T-typed integer linked list. So that's the specific implementation, meaning the content is primitive integer. For double, there will be double. For short, there will be short in the name, etc., etc. You can see that there is increase of the efficiency, not that huge because it's still linked list. There is still double linked list inside next pref. The situation is different for array lists. So this is the standard one. Here you have Trove, fastUtil in case of primitive integers, and you see, okay, it's consuming almost the same because there is just, what is the overhead? Just single object header for this T-int array list instance, nothing else, just single. In case of this is for every element there is another overhead and there is the reference, etc., etc. This is not the case for the Trove, for type-based, and it's almost 4 million of bytes, so almost 100% usage efficiency in both cases, compared to 23% here or almost 16% here. And that also applies to the maps. So last 3 lines are for maps. And you can see that for Trove and fastutils, we increase it from very small percentage of efficiency to almost half. It's not the optimal because it's related to the fact that there is that load factor. So we usually keep a lot of hash table empty. There are also 3 arrays instead of 2, etc., etc. And those are consuming memory. instead of just the single reference. In case of even fastUtil, we are using 2 arrays. So there are, in fact, if it is same, you can use this also if you are using objects. It will be faster, but still it's reference. Still with better efficiency. Another factor which is affecting collections during the runtime is resizing. Array list, maps. Array list has some backend arrays. If those arrays are already full, you need to create larger array, copy everything, and then add additional elements. The same is applicable to the map structure. You have backend hash tables. If the amount of element goes over the load factor, you need to create a larger hash table, copy the value. In that case, it's not the copy. You need to do rehashing. Insert again completely the elements, iterate over all elements, and insert them in. And that's the runtime overhead for the collections. So let's go through various collections, how it works. So this is the standard array list collection provided by Java by default. It solves the problem with the empty arrays. I've already mentioned it's using the static empty array representation. If you put there at least one element, the default size is 10. And it automatically grows using the strategy plus 50%. So it's 10, then it's 15, etc., etc. So it's increasing and increasing. It doesn't contain shrinking. If you remove elements, after you inserted, for example, 1 million elements, it will not decrease the backend array size, so still consume the memory. You have to call trim to size to shrink the backend array and copy remaining elements back to the original backend array. So those are those two problems there behind. And that copying, so if you know in your code that you are going to insert 1 million elements into some array list, you should reserve the capacity in the array list in advance. That's possible. During the creation, you can say, let's create array list directly with backend array size for capturing 1 million elements. And by that, you are removing that regular resizing and copy of the content. That's much faster, for sure. So let's look how it works for Trove and fastUtils. In this case, again, using default capacity 10. For fastUtils, it's using 16. There is one drawback. Maybe in the very last version, they already solved that, I don't know. Allocates immediately. So even if it is empty, it consumes 10 or 16. Growth strategy multiplied by 2. So power of 2, in fact. Initially 10, then 20, then 40, then 80, and so on. Both doesn't contain automatic shrinking. You have to manually use trim to size, like here, or trim. And you should, if you are removing a lot of elements, and then keep the remaining, you should use trim to size to free not used memory. How it works for the hash maps. Standard hash map collection. Hash table is initialized with the first element, so if it is empty, again, it's not existing. Default hash table size is 16, with default load factor 0.75. Capacity is then growing by multiplication of 2, so power of 2, in fact. 16, 32, and so on, 64. Implies rehashing, as already mentioned. It's iteration plus put operation on all previous elements. And hash table itself doesn't allow any shrinking at all, the standard one. So if you have a hash map where you put a lot of elements, then some of them are removed, and you keep hash map structure, that backend array or backend table is still very big. So if you would like to shrink it, you have to create new instance of hash map, smaller, insert all elements and replace the pointer to that. That's the only approach. In case of Trove, default hash table structure, because I said it's work with the prime numbers. The prime number 23 is the first one which is used. Load factor is 0.75. So if you provide a custom capacity, like I've mentioned for the array list, that's doable also for hash map, all this collection for performance. It searches for nearest bigger prime number for the capacity. The growth strategy is multiply by 2, but nearest bigger prime number. Again, rehashing implies iteration and put over all previous elements. So if you are going to insert 1 million of key value pairs and use just the default hash map or default Trove or default fast utils, it's the same. You are implying a lot of rehashing, a lot of inefficiency. So if you know I'm going to insert 1 million, let's create hash map supporting 1 million directly. On the other hand, the Trove contains auto compaction. If there is a certain number of removals, so it tracks that inefficiency. If it goes over some certain threshold, then it tries to shrink the hash table size and do the rehashing on the other size. So if you have a lot of insertions, removals, and you are using Trove, you can use also temporal disable of this feature. You create that structure supporting a lot of elements, do insertion, deletion, and finally enable that. You reduce a lot of computation load by that. This is summary for fast utils. Again, backend array allocated immediately. In this case, it's 16. Load factor is 0.75, so like a standard hash map. Custom capacity rounded to power 2, like a standard hash map. Growth strategy times 2. Again, rehashing requires iteration and put operation on all previous elements. And again, similarly to Trove, it supports auto shrinking. So it tracks the number of removed elements. If it goes under a certain threshold, it does the shrinking. It is possible that if you measure some application, you will find that you have a lot of map structures where you have either no element or one element only. In such case, it's much better to create some stub objects, which will you use for such cases. That stub object will contain just key and value, nothing else, and it implements the interface of map. And if you would like to insert another element, and there is already one, let's create a regular structure, insert that previous value and the new value. By that, you will save a lot of memory, because if you do some more complex system, you will find that there are a lot of map structures, but usually contains no elements or just single elements. So by that, you can optimize a lot of your application. And that was very last slide I have, so we saved some time today. So thank you for your attention.